Hello, ladies and gentlemen. Today we're going to be taking a closer look at Newton's third law of motion. But before we do, I'd like for us to review just real quickly what Newton's first two laws of motion say. Newton's first law of motion says that an object at rest stays at rest, an object in motion stays in motion in a straight line and at a constant speed unless acted upon by an unbalanced force. This law, of course, is also known as the law of inertia, inertia being the tendency of an object to want to continue in whatever motion it is currently in. Then there's Newton's second law. Newton's second law tells us that the acceleration of an object is dependent upon the object's mass and the force acting on the object. And there is, of course, a formula that is used to be able to calculate um, we can either calculate the acceleration or we can calculate the force or we can calculate the mass as long as we have the other two items. So we could say that acceleration is force divided by mass. We could also say probably the more common way to write the formula is F equals ma, force equals mass times acceleration, or as I like to shorten it to, FMA. All right. So, ladies and gentlemen, those are Newton's first two laws. Today, we're going to take a closer look at his third law. So, let's do that now. What does the law say? Well, it essentially says whenever one object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. So, we could also say for every force, there's an equal and opposite force. Perhaps you've heard it said in the past for every action, there's an equal and opposite reaction. That's not incorrect. I think the word force is a better word to use. It explains better what is happening rather than the words action and reaction, but we are going to use those terms. But for every force is an equal and opposite force, we can also say that all forces act in pairs. This is yet another way of stating Newton's third law. All right, so let's take a closer look at it now that we know what it says. So there is a force that is acting on an object, and we call that an action force. Go figure. And then the force that is reacting to that action force, of course, is the reaction force. So let's take a look at our swimmer here for just a moment. The action force is the swimmer's hands pushing on the water. As the swimmer's hand moves through the water, the hand pushes on the water. The reaction force is that the water is pushing back on the hands. Okay. So the hand pushes against the water pushes back against the hand. This is what causes motion. It is actually the reaction force that causes the swimmer to be able to move forward. If all we had was an action force, then the swimmer's hand would be pushing on the water, but it would just continue to push the water back, and the swimmer would make no progress at all. It's only because the water pushes back on the swimmer's hand that the swimmer is actually propelled forward. One really, really important point, and this gets really confusing for a lot of people, and is one of the reasons why, even though it seems like Newton's third law is really easy, because we say, for every action, there's an equal and opposite reaction, seems really easy to remember, right? For every force, there's an equal and opposite force. Uh, the problem is people get that confused a lot with the idea of balanced forces, which we talked about with Newton's first law, but it's different. So a lot of people think, well, if for every force there's an equal and opposite force, then nothing will ever change its motion. Either everything stays moving the exact same way it is, or everything continues to always stay at rest. But action forces and reaction forces are not acting on the same object. When we're talking about balanced forces, we're talking about a case where forces we're talking about forces that are acting on the same object. So we might be talking about a box and what forces are acting on that particular box. In the case of action and reaction, we're talking about a person's hand against the box, and then we're talking about the box having a force against the person's hand. So that not all the forces that are being talked about when we talk about Newton's third law are happening against the same are happening on the same object. Let's see if we can explain that a little more. In this case of the swimmer, the reaction force was exerted on the swimmer's hands by the water. Okay, the reaction force was exerted on the swimmer's hands. Well, let's see. I think I read that wrong the first time, but let me try again. The action force was exerted on the water by the swimmer's hands. The reaction force was exerted by the swimmer's hands by the water. Okay, so the two forces that we're talking about here, the action and reaction, one force is acting on the hands, the other force is acting on the water. These forces do not balance each other out because they are not acting on the same object. So they can't cancel each other out, and that's why the motion changes. All right, so another example where we can see Newton's third law at work, we've got a space shuttle, and the thrusters push the exhaust gases downward as the gases push the shuttle upward with an equal force. Okay, we'll show that again. So the rocket moves up or the shuttle moves up because the gases that are coming out of the shuttle push down uh, against the ground while the ground pushes up. And so the shuttle moves upward. All right, here we've got a rabbit. The rabbit's legs exert a force on the earth. The earth then pushes back with an equal force on the rabbit's legs. This causes the rabbit to accelerate upward. Or, well, okay, he didn't exactly go up, but, he went across. He accelerated. All right, let's take a look. We've got a baseball player hitting a ball with a bat. The bat is going to exert a force on the ball that is going to send the ball flying through the air. The ball, however, is also exerting an equal amount of force on the bat. Okay. It seems strange that the ball would be exerting the same amount of force as the bat. Keep in mind, there's still a lot of other forces going on in this situation. We're just narrowing it down to two of them, and those two happen to be equal. They are not acting on the same object, so they are not balanced, but they are equal. Okay? The bat doesn't move backward because as I said, there are other forces at work, such as the force of the batter's hands on the bat exerting a force. So there are a lot of different forces at work in this particular situation. Like I said, we narrowed it down to just two of them. All right, here's a rather odd picture. So we've got a red ball here that just fell to the ground. Go figure. What is it that pulls it to the ground? Well, gravity, of course, does. It pulls the ball toward the earth. This force is the action force exerted by the earth on the ball. There is, however, an equal and opposite force. Gravity also pulls the earth toward the ball. That is the reaction force exerted by the ball on the earth. Because remember, gravity works both ways. All objects that have mass have a gravitational pull. And so the ball is pulling the earth towards it in the same way that the earth is pulling the ball toward it. Okay, remember that gravity is the force of attraction between objects that are due to their masses. So not only does the ball want to be pulled towards Earth, the Earth wants to be pulled towards the ball. Who is going to win that battle? Well, we know, of course, the Earth is going to win that particular battle. Okay, the action force of the gravity on the ball falling to the Earth because of gravity um, But why don't you notice the effects of the reaction force? Why don't we notice the Earth being pulled upward? Well, if we go back and we think about Newton's second law, the mass of the Earth is much more than the ball, so the acceleration is less. It's too small that you can't actually see or feel the acceleration. We could even think back to Newton's first law, the idea of inertia. It's going to take a lot more force to overcome the inertia of the Earth rather than the inertia of the ball. I know, it's kind of confusing. I get it. Again, Newton's third law is the easiest to kind of memorize, but I think in a lot of ways it's the hardest one to understand. Let's go back and take a look at Newton's laws. Newton's first law. We know, of course, Newton's first law is uh, that an object at rest stays at rest, an object in motion stays in motion in a straight line and at a constant speed unless acted on by an unbalanced force. What is another name for it? That's right, the law of inertia. What is inertia? Well, it's the tendency of an object to continue in the motion that it's in. What is Newton's second law? Well, we know that Newton's second law tells us that the acceleration of an object is dependent upon the object's mass and the force being exerted upon it. We know that as mass increases, acceleration decreases. As a force decreases, acceleration also decreases. Newton's third law. Newton's third law tells us that for every force, there's an equal and opposite force, or forces work in pairs. And then we looked at some examples. Some examples like the swimmer and their hands, the bat and the ball. We're going to look at some more examples in our next class period as well. So just kind of keep in mind that you'll be taking a look at some other examples, and hopefully at the beginning of uh, in one of our future classes, we'll also have an opportunity to do an activity that demonstrates Newton's third law as well. All right, ladies and gentlemen, I hope that you have a fantastic rest of your day. We will continue to explore Newton's third law as well as all three of Newton's laws. And we will soon be preparing for a test as well. Thank you.